So, hope you guys are doing well. Let me just a sec. Yesterday, we utilized the formula Coulomb's law in a few different situations to help give you an idea of what places it might show up on homework and test questions. Today, we're going to expand on it a little more, probably wrap up the bulk of the Chapter 15 content. Tomorrow we will meet on campus for lab, and I'm gonna say I'll send this out in an email so that you guys have it in writing and you don't have to just remember me saying it. Let's meet at the room at about 11. It'll give me more time to set up, and if it's just a very small group, we'll probably get through both labs pretty quickly like we did last time. We can still plan for an hour lunch break just in case, but if we just work through the afternoon to get it done, that'll be just fine too. So, again, I'll send this in writing, but let's plan on meeting at 11 so I have more time to get everything ready before we get started. So, today we'll continue on through Chapter 15. Tomorrow is lab day. Friday, we'll have a kind of chill, just pop in and do homework questions kind of day. Make sure that you guys are doing all right with the Chapter 15 material, and the next week we'll move on to Chapter 16. And let me know if you have any issues, needs, requests, concerns, etc. about any and all of this information. And if not, we'll get started continuing on. I'm taking one quick second to edit something. Okay, never mind. Okay. Okay, so we've been utilizing the formula Coulomb's law. I'm going to tab back to its introductory slide just to make sure we're on the same page there. The formula for the electric force between two charged particles or charged objects, referred to as Coulomb's law, F equals KQQ divided by R squared. Now, I'm hoping that before we started using it, before we even started talking about what the terms in it mean, my hope is that this formula might have seemed kind of familiar to you. Not necessarily the variables that are in it, but kind of its structure, what sorts of variables are in what place, sort of the way that the formula looks, the way that it operates. I'm hoping that looked kind of familiar to you. And the reason that it might is because you, if you remember from Physics 1500, have used a very similar formula in the past. Currently, what I have on screen, Fg equals big G times M1 times M2 divided by R squared, that is the universal law of gravitation formula. That is the formula that is used to calculate the gravitational force between any two objects with mass. And if you'll kind of mentally compare that to Coulomb's law, they both calculate forces. They both involve some constant, K for Coulomb's law and big G for gravitational law. Then you multiply that constant by some aspect of both objects involved. In Coulomb's law, you multiply by the charge of each object. In gravitational, you multiply by the mass of the two objects. And then you divide by the distance between them squared. So the formulas have identical structures. The only difference is, for gravitational law, you plug in big G and masses. For Coulomb's law, you plug in K and the charges instead. The formulas are basically identical. They're twins, at least, or fraternal twins, maybe. And the reason for that is because both gravity and the electric force are very similar. They work very similarly. And in a lot of ways, they're considered to be members of a family together. Depending on how much physics and or chemistry you've gotten through, you might have become aware of a concept called the four fundamental forces. These are, at least by physicists, regarded as the four literal forces that hold most of the universe together. Without these four forces being as strong as they are, or not, the four forces I'm about to mention are responsible for the bulk of the operations of the universe as we understand it. And without them existing, or without them being as precisely tuned as they are, the universe as we currently understand it wouldn't be possible. Those four forces are gravity, the electromagnetic forces, the weak nuclear interaction, and the strong nuclear interaction. They are all literally forces, and they all literally hold the universe together. Literally everything we know kind of hinges on those forces acting the way that we do. And I bring them up to point out that on that list we have both gravity and all varieties of electromagnetic forces. Technically, the electric force is itself also part of a family of forces, but that family is still related to the gravitational force by virtue of being one of the fundamental forces. And that's why they work so similarly. They are a family. Charge and mass are both just different properties that matter can possess. Mass is how much physical stuff is present inside the object. Charge is the object's electrical properties. And every single piece of matter has some innate mass to it and some innate charge to it. And these two different formulas just represent how those properties of matter interact with themselves. The gravitational formula tells us that mass will exert an inward force on all other mass, and Coulomb's law, the electric force formula, tells us that all objects with charge will exert force on all other objects with charge. The primary difference between the two is the fact that charges can be positive or negative, whereas gravity can only be inward positive facing. Mass can only be positive. You either have zero mass, in which case there's no gravity, or you have some mass, in which case there's positive inward gravity. So gravity only has one direction it can point in. It always points inwards. Two objects with mass will always attract to one another, and that's why Earth's gravity holds you to the surface of planet Earth. Your mass is literally attracted to the mass of the planet. Electrically, though, charges can be either zero, positive, or negative. With mass, there's only 0 and positive, but with charge, there's negative 0 and positive. And that means that the electric force can point in one of two different directions. It can either point inward for positive and negative attraction, or it can point outwards for like sign repulsion. That is the primary difference between the two. It's just that one of them has a bigger variety of directions that it can point in. But other than that, both gravity and the electric forces, and eventually later when we talk about the magnetic forces, all behave very, very similarly. And specifically, both gravity and electromagnetism accomplish what they do because of fields. You've probably heard the term gravitational field, maybe in reference specifically to Earth's gravitational field. And the math that's on screen right now is basically a slight editing or a simplification of the universal law of gravitation formula. Instead of calculating the force that Earth's gravity exerts on an object, the formula has been slightly modified to calculate the gravitational field at a specific spot, a specific distance from Earth's core. It's not the force acting on one object, it's the field exerted at a specific location. And all objects with mass exert a gravitational field. That includes yourself. And Earth's gravity works on our bodies in that Earth, it has a very large amount of mass. It's creating a very big gravitational field. We are currently inside of that gravitational field. And that means that each individual human, since they are also made out of mass, they also have their own gravitational field. And in general, whenever two fields of the same type overlap, so whenever Earth's gravitational field overlaps with your own body's gravitational field, so Earth's field is very big, and your body and its field are inside of the Earth's field. Whenever two fields of the same type overlap and interact, that's when the force of that type is generated. So gravitational force is created when Earth's gravitational field overlaps and interacts with your own gravitational field. So all objects with mass create gravitational fields, and this slight edit to the formula tells us how to calculate Earth's gravitational field. The field is what then creates the force on an object. And so we could use this formula to find the gravitational force by multiplying the mass of an object by Earth's gravitation, by what we get from this formula for Earth's gravitational field. And you've already been doing that, as it happens, because if you use this formula, big G times Earth's mass divided by Earth's radius squared, to try to determine the strength of Earth's gravitational field on Earth's surface, you get 9.81 meters per second squared. This is the formula that gave us that value of 9.81 meters per second squared. You take this formula, you multiply it by your mass, and that tells you the gravitational force of Earth on your body. This is where that number comes from. This is how it was derived. So 9.81 it represents the strength of Earth's gravitational field on Earth's surface. The closer you get to Earth's core, the bigger that number gets. The further away from Earth you go, the weaker that number gets. And I'm bringing all this up again to draw a direct comparison to the electric field, to electricity and magnetism. Currently on screen is the same basic process that was taken to edit the gravitational formula, but applied to Coulomb's law instead. So right here, we have the Coulomb's law equation. Force electric equals kQq over r squared. This has been edited slightly to, instead of calculating electric force, is now able to calculate the strength of a single object's electric field. So gravitational fields create gravitational force, when two fields overlap. Electric fields create electric force when two electric fields overlap. So imagine again, you're a kid on the playground equipment, you're inside the plastic slide. The slide, if it's built up a charge, has an electric field, and therefore inside the slide there's a big electric field acting on everything, and it will interact with your body's electric field to lift your hair up and create that effect. So, objects with charge create electric fields, just like objects with mass create gravitational fields. And similarly, when electric fields overlap, that's when you create electric force. When gravitational fields overlap, that's when you create gravitational force. All the same logic applies between the two. The only real difference between the electric fields and gravitational fields is electric forces can point in two different directions, whereas gravity can only point inwards. Now, currently on screen, I've simplified the formula a little bit. This is just to show the formula for electric field. All objects with charge generate some amount of electric field. And this variable E right here is the strength of an object's electric field. The primary formula for electric field is K times the magnitude of the source of a charge divided by R squared. If you want to figure out how strong an electric field something is giving off, you need to take our big K constant here. It's the same K constant from Coulomb's law. Multiply it by the strength of the charge in question, and then divide it by how far apart from that object you are examining. Fields get weaker, all fields, doesn't matter what type, get weaker the farther away from the source you are. Earth's gravity gets weaker the farther away you are from Earth. Similarly, the field created by a charged particle gets weaker the further that you go from that particle. So all electric field calculations are from a certain location. This formula specifically calls for us to pick a spot a certain distance away from the source, and this formula tells us the electric field at that specific spot. If you drift closer or further away from the source, the field value changes, and you'd have to calculate again. But there's a second formula for calculating electric field strength as well. This formula on the end here, KQ source divided by R squared, this is how you determine the strength of an electric field if you know what's creating that field in the first place. So, say you put a proton in a box, you know that proton is creating an electric field, and you want to know how strong that field would be so far away from that proton. You can use this formula to determine the field that proton creates. But sometimes you don't always know what is creating an electric field. Sometimes in nature, electric fields just exist, and you don't always know what their source is exactly. So instead, there's a different formula that can be used if you don't know the source of the field. And that formula is this other part right here in the middle. Historically speaking, and I'm going to tab away for a second to show a different picture. This image currently on screen is a very old school method of visualizing the electric field that an object gives off. What you're physically seeing here is a picture of this black dot in the middle is a piece of iron that has been given an electric charge, and it is currently submerged in oil. That oil has been filled with iron shavings that begin reacting to the metal's electric field, and they start lining up to represent the field itself. And historically speaking, if you knew that an electric field existed, but you didn't necessarily knew where it was coming from. So say we were examining this region of space that I'm boxing around, and we didn't necessarily know where this electric field was coming from. We just wanted to know how strong it was. Historically, what scientists would do is they would put a test charge in that area. So if this is the area that we're testing, they would drop an electron right in the middle there. They know this field exists, and they just put an electron in that little zone to see what happens to it. That electron is a test charge. We are literally testing to see what happens to that charge. And when you put a charged particle in an electric field, there's going to be some amount of electrical force, like when you put mass in a gravitational field. And so they watch what would happen to that test charge, see what direction it starts moving in, try to measure the magnitude of the force that's acting on it. And that's where this additional part of the formula comes in. This version of the formula, electric field equals electric force divided by test charge. What they would do with this information is, if they could measure the force that the field exerts on something and divide by the magnitude of the charge that they put in the field. So say if they put in an electron and there was 10 newtons of force acting on that electron, they would divide 10 newtons of force by the charge of a single electron. And that would also tell them the magnitude of the electric field. It would tell them what the strength of the field would have to be to create that result acting on the electron that they put in there. So the two different versions of this formula exist to sort of give two different methodologies for determining the strength of an electric field. One, if you know the details of the field's source, and the second as a way to test a field regardless of knowing what its source was. And it's also worth noting, let's see if I can do this. That didn't work as intended. If you just were to look at the part that I'm currently circling right now, FQ over Q equals KQ over R squared. That formula is basically Coulomb's law. They just took one of the Q's from the right side and sent it to the denominator of the left side. So it really is still the same formula. The way, like the formulas that we use to calculate field come directly from Coulomb's law. They're both still interconnected, and you can still relate them as it's currently shown on the screen. The E part on the front is just the representation of the variable for electric field itself. So big capital uppercase E, if it shows up in a formula, is electric field. It represents the power of an object's electric field, or the electric field within a certain location. Electric fields will change based on how far away you are from what made that field. And I'm realizing it's not actually on this slide, so I'm going to change that real fast. E field is measured in units of newtons per coulomb. So, the unit of electric field is newtons per coulomb. Literally, the unit is how many newtons does it exert on 1 coulomb charge. So, this is technically a new variable, and these are the formulas that we can use to calculate it. And this is the unit that it is measured in. Now, electric fields are, well, really all fields, gravitational, electric, magnetic, are kind of hard to quantify at times given that humans can't see them. No, humans have no inherent way of detecting electric fields, magnetic fields, other than observing the effects that they have around us. We can't even really observe gravitational fields directly, we just observe the forces that they create. So all fields, as a result, are kind of hard to visualize. It's kind of hard to tell that they're there, except for what they do on other things. They're impossible to identify other than seeing the effects they cause on charged particles or objects with mass or magnetic objects. So over the years, humans have had to come up with... Oh, well, now it's working. Humans have had to come up with different ways of drawing those electric fields. How do we represent them in a way that makes sense to the human brain? How do we show that they exist on drawings? The first way that humans could ever try to see an electric field is, again, this method that this image that I showed earlier. This is, again, a piece of iron that has been electrically charged, surrounded on all sides by iron shavings floating in oil. And the iron shavings are lining up. They are moving in such a way that they are lining up with the field lines of the electric field. All fields, at least in drawings and in our minds, we represent fields in terms of field lines. The lines are the way that humans try to draw where the field is, how strong it is, what direction the field is pointing in. And this particular image here is showing us that the field lines, the electric field being given off by this particular object, is radiating outwards from the object creating it in straight lines. So all objects that have charge, if they're completely by themselves, create field lines outward in all directions, in straight lines if it's by itself, which is fine and dandy. It makes sense. It's kind of like it's radiating electrical power in all directions. That's something that the human mind can kind of wrap its head around. Things start getting a little weird when two different objects with charge are both separately creating electric fields in the same space. So previously there was just one charged object, but now we have two charged objects. In this particular drawing, one of them is positive and one of them is negative. So the scientists involved very specifically made one of these iron balls positive and one of them negative. And since both of these objects are creating fields in the same general area, those fields overlap here in the middle. Now, when fields of the same type overlap, that's when you get a force between those two types of fields. Again, on planet Earth, your gravitational field overlaps with Earth's gravitational field, and that's what creates gravitational force on your body. Here, we have electric fields being created by two separate objects that are overlapping, and that's going to create electric force. So there is electric force between these two things. We could use Coulomb's law to calculate the electric force between these two objects. What I want to focus on in this specific moment, though, is what these fields look like when they overlap. These field lines, rather than continuing on in straight lines and kind of literally overlapping, as if you just drew one line and then drew another line over it, they start bending. What we have here is one positive charge and one negative charge. And the positive charge is emitting field lines outward from itself in all directions. And negative charges, given that they are negative and therefore opposite of a positive charge, negatives, rather than sending field lines outward, pull field lines inward. So the positive charge is sending field lines out of itself. The negative is pulling field lines into itself. And by themselves, if these two charges were completely separate, that wouldn't really look any different. It's still straight lines. But when they're together like this, we can see that one of them, the positive, is feeding into the negative. The field lines coming out of the positive, rather than continuing out in straight lines, are getting redirected and being pulled into the negative end. This is kind of similar to the way Earth's magnetic field works, if you've seen diagrams of that. It's generally regarded that Earth's magnetic field also has field lines. Magnetism works a lot like electricity. It also has field lines. Earth's magnetic field lines come out of one pole, circle around the Earth, and then go back into the other pole. Because one pole is magnetic positive, one pole is magnetic south. Magnetic north, magnetic south. The two poles are opposite each other. One sends lines out, the other pulls lines in. And because of that fact, you get the sort of cyclical nature there that creates the net effect of Earth's magnetic field. And here, in this drawing, I'm going to try to draw some more lines here to represent. Here, we again see field going from positive to negative. And this bending of the lines, normally the lines would just point straight under normal circumstances, but because of the influence of the second object, they start bending, and that bending is what creates the electrical force in this specific case. Bending of the lines creates force. Again, this is what happens when the fields are overlapping. The lines sort of add together to create this bent effect rather than just moving in straight lines. And again, this picture was originally taken by each of these little dark spots represents iron shavings floating in oil. And so each individual iron shaving is itself a straight piece of metal, and each one is just kind of bending in a different direction to form these bent curves. And so this is what it looks like when the two objects have different charges. Positive charges emit fields out of themselves. Negative charges pull fields into themselves. And that kind of cooperation is what allows for the two to attract to one another. Things get a little weird. Moving on to a different slide now. Things get a little weird when the two charges are the same. So let's say these are two separate positive charges. When the charges were opposite each other, one creates field, one absorbs field, that can create a nice kind of a clean continuum. Comes out of one, goes into the other. If there's two positives, we already know before looking at the field lines that we're going to have a different result if it's two positives, because like charges repel. But this visualization here is the reason why there's a difference. So with the positive, in the previous version, with the positive and the negative, since one emits field and one absorbs it, that creates the continuum that allows for attracting force. This, since these two oppose one another, it's the same charge and they're going to repel, they are both emitting field right now. They are both sending field out from themselves. And those field lines are literally going to collide and push apart. And so rather than one feeding into each other, they literally butt up against each other and get redirected as a result. It's like if two footballs were thrown at each other perfectly and they collide in midair. they're not going to move through each other and continue onwards. They're going to bounce off of each other and get redirected. So, like charges, their field lines just collide and get redirected, and sometimes they kind of fizzle out. This little nebulous zone in the middle here, the iron shavings here aren't really pointing in one direction or another because all the field lines here are kind of colliding and the field kind of stops existing right here. The lines are a lot better defined closer to the objects and in the spaces where the two field lines aren't directly affecting each other. So, like charges, their fields, instead of cleanly sort of transitioning one into the other, they literally oppose each other, butt up against each other, crash and redirect, and that's why like charges repel. They're fundamentally incompatible from each other. Two positives are both giving field outwards. Those fields will literally push up against each other and redirect. Meanwhile, two negatives, they're both pulling field inwards, but they're both trying to pull something inwards that doesn't really exist, and since there's no positive creating field, and as a result, they also don't really mix very well, and they will also repel from one another. So, this is how humans have done their best to try to represent field lines over the years. Again, we have to use shortcuts like this to be able to see them, since they aren't normally visible to us. And from these drawings, we've been able to create additional drawings, rather than submerging particles in iron shavings floating in oil. This is just a drawing that someone made to try to represent the field lines being created by a positive and a negative in three-dimensional space. The goal of this picture is we can see the positive charge giving off field in all directions, and in all of those sides, the field is slowly being bent towards the negative particle. And so this is how field lines are drawn. There's certain rules that humans have come up with to try to represent how to show these field lines. Namely, if two fields are existing in the same space, their field lines don't ever cross each other like an X. They will always either feed one into the other and bend if they're opposite charges, or they will butt up against each other and repel if it's like charges. We'll deal more with this information for lab next week when we start doing the electricity labs. There's one lab that will involve trying to sort of quantify electrical fields generated in space. But I wanted to go ahead and show the graphics to try to represent what these fields are and how we try to measure them. Oh, one other thing. The amount of field lines created by an object depends on how strongly charged that object is. The more charge something has, the more field it creates, the more field lines it sends out. So this drawing here represents what happens when one charge is just much, much bigger than the other charge. Specifically, the red particle here is 2 times the charge as the negative particle. Now, the negative particle has 1, 2, 3, 4, 5, 6, 7, 8 field lines coming off of it. Whereas the positive particle has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 lines coming off of it. It's twice as strong, it creates twice as much field, so it has twice as many lines. The negative charge only has 8 lines, so that means that of the positive particle's 16 lines, 8 of them feed directly into the negatives, whereas that leaves 8 other ones that don't connect straight to it. This charge is strong enough that it creates more field than the negative one, and as a result, some of its field is still allowed to sort of go off into space without being pulled into the negative. So, stronger charges create more field. That's all this is trying to visualize. Now, I want to look briefly at this kind of conceptual example. We're not actually going to do any math for this one. I just want to look at it conceptually. There's 3 charges presently here in this particular example. We have one negative charge, a second negative charge of the same strength, and then one positive charge that is twice as big as either of them. And all of these charges are going to be creating electric field. They all create field. They're all sending out field lines in all directions. And that means that at this hypothetical spot that I'm Xing over right now, all of them are creating field lines that will somehow eventually end up at this particular spot. Each of them separately creates field that would exist here, but now that they are all here with each other, all of their fields are going to overlap at this spot. And the question is, what will the resulting field at that location look like because all of these different fields are overlapping? Now, electric field adds up linearly just like electric force does. In previous examples we've looked at, when multiple charges are exerting electric force on a specific third charge, the forces involved still add up normally. You have to keep in mind vector direction, but the charges do still add up. The forces add up. And that's the same for electric field. And numerically speaking, the magnitude of the field right here will be the sum of this charge's magnitude at this spot, this charge's magnitude at this spot, and this charge's magnitude at this spot. But because they all have different signs to them, each of those separate fields are going to point in different directions. This first charge here, I'm going to label it number 1. This first charge, since it's negative, and negative charges pull field lines into themselves, its field lines at this spot are going to point to the left. The point that I'm labeling charge number 2, it's also negative, so it's also going to pull field lines into itself. So the field it creates at this spot is going to point down. The positive charge, positives create fields out of themselves, so its field lines are going to point out in this direction from the test location's perspective. It's exerting field outwards from itself, and if we just draw a straight line from here to that spot, the arrow would continue pointing this way. So the 3 separate arrows that we would add up together to try to create the net field at this particular spot are this arrow, and this arrow. And so to find the net field at this particular location, we would need to add these 3 fields up together. Now, even though this charge is the single biggest one here, the other 2, the 2 negatives, are still closer to this particular location than the third one is, just because of the way that squares work. Charge 1 and charge 2 are closer to this location than charge 3 is. And as a result, they're going to have a stronger effect on that spot, even though charge 2 is bigger. Charge 2 may be twice as big, but there's still 2 negative charges here that add up to the same magnitude of charge, but negative, and they're closer. As a result, the net field at this particular location there we go. Once we add all the field lines together, is going to point in the D direction because There's just more negative here than there is positive here. Or rather, the negatives are closer to that location. This is all potentially kind of difficult to visualize, and that's why we're not really doing any math for this right now. I'm just looking at the conceptual part of how electric fields overlap and create electric force. These slides here, if you were following along with these notes or if you look at them separately from class time, there's lots of different pictures here to represent different objects creating electric fields, and objects of different shapes, objects of different charge levels. And we'll actually do more work looking at the fields themselves in lab next week. And I think we might actually go ahead and call a break right here, because that's actually all of the information that's present on the Chapter 15 homework. I don't want to overload you on one day. How does this feel? The field lines themselves, I think, are probably the weirdest part of this particular chapter. And the field lines in general will continue to be kind of weird because as time goes on, we're also going to be looking at magnetic field lines and how magnetic fields interact with electric fields. So if the field lines, if fields in general feel kind of weird to you, that's allowed. That makes complete sense. They're a strange thing, especially since, again, humans can't really see them, so you might not have a whole lot of experience thinking about things in terms of field lines. It's going to be... Right now, I just wanted to let the information sink in, and we'll start applying it more in future chapters. Let me know how this feels. Let me know if you need anything. We'll go ahead and break here for today, because that's all the information I wanted to get through today. Tomorrow we'll meet for lab, and as a reminder, let's meet in the lab at 11. We'll do 2 labs. I don't expect them taking very long each, so we'll hopefully be done by about 1 or 2 in the afternoon. Let me know if you have any issues getting to campus or any scheduling conflicts. And we'll meet again for Friday. We'll probably talk about a few... We'll try to wrap up Chapter 15 on Friday and then transition into giving you guys some free time to work on the homework while I'll be available for questions. I won't be in the call... After we break here right now, I won't be in the call for much longer today because I have some appointments coming up, and I apologize for that. So if you have questions, ask them now or send them to me via email, or when we meet again later this week will be a good time to ask them as well. I'm rambling at this point, as I tend to. Cut me off if you need something. If no one has any particular questions right now, we can go ahead and call things here for today, and I will see you tomorrow. Thank you, guys.